Right now, as you sit there listening to this, about 100 trillion neutrinos are passing through your body every single second. They're streaming through your skin, through your bones, through every atom you're made of, and not one of them will touch you. Not one. They come from the heart of the sun, from exploding stars, from the very first second after the Big Bang. They pass through the entire Earth as if it isn't there. In your entire lifetime, out of the trillions upon trillions that will fly through you, maybe one, just one, will ever make contact with an atom inside your body. This is the story of the neutrino, the ghost of the particle world, and why the universe's most abundant matter particle barely knows you exist. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you already understand without thinking about it. You can touch things. You pick up a glass of water and you feel it in your hand. You press your fingers against a table and the table pushes back. You step on the ground and the ground holds you up. This seems obvious. This seems like the most basic, unremarkable fact about reality. But it's actually extraordinary. And understanding why you can touch things is the first step toward understanding why neutrinos can't. Everything around you, the chair you're sitting in, the device you're listening on, your body, the air in the room, is made of atoms. Atoms are the building blocks of all ordinary matter. Every element on the periodic table is defined by its atoms. Hydrogen, the simplest element, has 1 proton and 1 electron. Carbon, the basis of all life on Earth, has 6 protons, 6 neutrons, and 6 electrons. Iron, the element that makes up most of Earth's core, has 26 protons, 30 neutrons, and 26 electrons. There are 92 naturally occurring elements, each with a different number of protons in its nucleus, each with different properties, and all of them built from the same 3 basic components: protons, neutrons, and electrons. An atom has 2 main parts. At the center is the nucleus, a dense clump of protons and neutrons packed together incredibly tightly. Surrounding the nucleus at a much greater distance are the electrons. Now here's what's remarkable. The nucleus is tiny, unimaginably tiny compared to the atom as a whole. If you enlarged an atom to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. The electrons would be like gnats buzzing around the outer seats. Everything in between would be empty space. This means that matter, the stuff you think of as solid, is overwhelmingly nothing. Your body, which feels so substantial, is almost entirely empty space. The atoms that make you up are almost entirely empty space. If you could somehow remove all the empty space from every atom in every human being on Earth, all 8 billion of us, the remaining matter would fit in a volume smaller than a sugar cube. So if atoms are mostly empty space, why does the world feel solid? Why can't you walk through walls? The answer has nothing to do with physical material blocking physical material. It's because of a force, a fundamental force of nature, and that force is the electromagnetic force. When you press your hand against a table, the electrons surrounding the atoms in your skin repel the electrons surrounding the atoms in the table surface. This electromagnetic repulsion creates a barrier that your hand cannot penetrate. Nothing is actually touching in the way you intuitively imagine. It's all forces, all fields, all electromagnetic interactions at a distance. The solidity of everything you have ever touched is an electromagnetic illusion. real in its effects, but fundamentally a product of charged particles pushing against each other across empty space. This leads us to something essential. The universe operates through 4 fundamental forces. Just 4. Every interaction between every particle in the entire cosmos is governed by one or more of these 4 forces. Understanding them is critical to understanding neutrinos, because what makes neutrinos so extraordinary is which of these forces they respond to and which they ignore entirely. The first force is gravity. Gravity is the one you know best. It's the force that keeps your feet on the ground, that keeps the Earth in orbit around the Sun, that holds galaxies together. Gravity acts on anything that has mass or energy. It has infinite range. It reaches across the entire observable universe. The Sun's gravity holds Neptune in orbit at a distance of 4.5 billion kilometers. The Milky Way's gravity holds its hundreds of billions of stars together across a span of 100,000 light years. But here's the thing about gravity that most people don't appreciate. It's weak. Incredibly, almost absurdly weak. It seems strong because you're standing on a planet with a mass of about 6 trillion kilograms, and all that mass is pulling you down. But the gravitational attraction between 2 individual subatomic particles is essentially nothing. The gravitational pull between 2 protons is roughly 10 to the 36th power times weaker than the electromagnetic force between them. That's a 1 followed by 36 zeros. Gravity matters at cosmic scales because it always attracts, it never cancels out, and it adds up over enormous amounts of matter. But at the scale of individual particles, gravity is irrelevant. It's the weakest force in the universe by an almost incomprehensible margin. The second force is the electromagnetic force. This is the force that actually governs your daily life, far more than gravity does, even if you don't realize it. The electromagnetic force acts between particles that carry electric charge. Protons carry positive charge. Electrons carry negative charge. Opposite charges attract. Like charges repel. This is the force that holds atoms together. The positive protons in the nucleus attract the negative electrons, keeping them bound in their orbits. It's the force that holds molecules together through chemical bonds. It's the force responsible for all of chemistry and all of biology. When you see light, you're detecting electromagnetic radiation. When you listen to a radio, you're picking up electromagnetic waves. When your nerve cells fire, they're using electromagnetic signals. Every color, every sound your ears convert from pressure waves transmitted through electromagnetically bonded air molecules. Every sensation of touch or heat, all of it is electromagnetic. This force has infinite range, like gravity, but it's vastly stronger at the particle scale. The electromagnetic force is what makes the world tangible. It is the reason things feel real. The third force is the strong nuclear force, sometimes just called the strong force. This is the most powerful force in the universe, but it operates over an incredibly short range, only about the width of an atomic nucleus, roughly 10 to the negative 15 meters. That's about 1 quadrillionth of a meter. Beyond that distance, the strong force effectively ceases to exist. The strong force is what holds the nucleus together. Think about this for a moment. Protons are all positively charged. They should repel each other electromagnetically. A nucleus with 2 or more protons should fly apart instantly because of the electromagnetic repulsion. But it doesn't, because the strong force overpowers the electromagnetic repulsion at these tiny distances. The strong force binds quarks together to form protons and neutrons. And it binds those protons and neutrons together to form nuclei. Without it, no nucleus heavier than a routine hydrogen could exist. There would be no carbon, no oxygen, no iron, no rocky planets, no life. The strong force is the reason matter has the complexity it does. And then there's the fourth force, the weak nuclear force. This is where our story truly begins. The weak force is unusual compared to the other three. It doesn't hold anything together. It doesn't attract particles to each other the way gravity and electromagnetism do. It doesn't bind structures the way the strong force does. Instead, the weak force is responsible for transformation. It allows one type of particle to change into another type. The weak force is what drives a specific kind of radioactive decay called beta decay, where a neutron inside a nucleus transforms into a proton, emitting an electron and, as we'll discover, a neutrino in the process. The weak force operates over an even shorter range than the strong force. Its effective range is about 10 to the negative 18 meters, roughly 1,000 times, smaller than the diameter of a proton. If a proton were the size of a city, the weak force would reach across a single room inside one building. The weak force is also, true to its name, much feebler than both the strong force and the electromagnetic force at the particle scale. It's stronger than gravity between individual particles, but compared to the other two forces that govern atomic and nuclear physics, it is remarkably feeble. Now, here's the crucial point. Different particles respond to different forces. What determines how a particle behaves, how it interacts with the world around it, is which forces it feels. Protons feel all four forces. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They contain quarks, so the strong force acts on them. And they participate in weak interactions. Protons are thoroughly sociable particles. They interact with everything. Electrons feel 3 of the 4. They have mass, so gravity acts on them. They have electric charge, so electromagnetism acts on them. They participate in weak interactions, but they don't contain quarks, so the strong force doesn't act on them directly. Still, 3 out of 4 forces is plenty. Electrons interact readily with the world. And then there are neutrinos. Neutrinos are in a category almost by themselves. They have a tiny amount of mass, so technically gravity acts on them, but their mass is so minuscule that this gravitational interaction is utterly negligible for any practical purpose. They have no electric charge whatsoever. 0. This means the electromagnetic force, the force that governs almost everything in your daily experience, the force responsible for chemistry, biology, light, and the solidity of matter, simply does not apply to neutrinos. They are blind to it. They also don't contain quarks, so the strong nuclear force has no hold on them either. The only force through which neutrinos can meaningfully interact with other matter is the weak nuclear force, the one force with the shortest range and the lowest interaction probability. This single fact is why neutrinos are ghosts. The story of how we came to know about neutrinos begins with a crisis in physics. In the early 20th century, physicists were carefully studying beta decay. In this process, a radioactive nucleus emits an electron and transforms into a different element. For example, a carbon-14 nucleus decays into nitrogen-14. One of its neutrons has turned into a proton, and an electron flies out. The problem was energy conservation. The total energy before a reaction must equal the total energy after. This is one of the most fundamental laws in all of physics. It's not a suggestion. It's not an approximation that works most of the time. It's an absolute rule, verified in every experiment ever conducted, a cornerstone of the entire edifice of physics. If energy conservation fails, almost everything we know about the universe comes into question. But when physicists precisely measured the energy of the electrons emitted in beta decay, they found something deeply disturbing. The electrons didn't all come out with the same energy. They had a continuous spectrum of energies, ranging from nearly zero up to some maximum value. This was wrong, profoundly wrong. If a specific nucleus decays into a specific product nucleus and emits one electron, the energy balance should be exact. The starting energy is fixed. The ending energy is fixed. The electron should carry away the difference, always the same amount, every single time. But measurements showed otherwise. Some electrons came out fast, carrying nearly all the available energy. Others came out slow, carrying barely any, and everything in between. A smooth, continuous distribution of energies. It was as though the universe were randomly deciding, for each individual decay, how much energy to give the electron. Sometimes a lot, sometimes a little, with no apparent pattern or reason. The implications were alarming. If the electron was carrying less than the full available energy, where was the rest going? Physicists checked for gamma rays, high-energy photons that might be carrying away the missing energy. They found none. They checked for recoil energy in the nucleus itself. The numbers didn't balance, no matter how carefully they measured, no matter how precisely they accounted for every form of energy they could think of. There was always some energy unaccounted for. It simply vanished. The books didn't balance. And in physics, the books must always balance. This was a genuine crisis in the foundations of physics. Not a minor discrepancy, not a measurement artifact, but a fundamental challenge to one of the most sacred principles in all of science. Some brilliant physicists, including Niels Bohr, one of the fathers of quantum mechanics, suggested that perhaps energy conservation simply didn't hold at the subatomic level. Maybe it was only an approximate rule, valid statistically for large collections of atoms, but not for individual nuclear reactions. Bohr was willing to abandon conservation of energy. That's how serious the problem was, when one of the greatest physicists in history is prepared to throw out one of the most fundamental laws in physics. You know the situation is desperate. One physicist in particular found this idea intolerable. Wolfgang Pauli, an Austrian theoretical physicist known for his extraordinary intellect and his famously sharp tongue, he once dismissed a colleague's theory as not even wrong, meaning it was too vague to be tested, refused to abandon energy conservation. In December of 1930, Pauli wrote a now famous letter to a group of physicists attending a conference in Tübingen, Germany. He addressed them as "Dear radioactive ladies and gentlemen," and proposed what he called a desperate remedy. He suggested that during beta decay, alongside the electron, another particle was being emitted. A particle so elusive, so reluctant to interact with anything, that no instrument could detect it. This particle, Pauli argued, carried away the missing energy. It had to be electrically neutral, because the electric charges already balanced without it. It had to have very little mass, possibly none, because the maximum energy of the emitted electrons nearly accounted for all the available energy. And it had to interact extraordinarily weakly with matter, because nobody had ever seen any trace of it. Pauli initially called this hypothetical particle a neutron, but that name was soon claimed by the much heavier neutral particle James Chadwick discovered inside atomic nuclei in 1932. The Italian physicist Enrico Fermi then renamed Pauli's particle the neutrino, which in Italian means little neutral one. But Fermi did far more than just name it. In 1933 and 1934, he developed a comprehensive theoretical framework for beta decay that incorporated the neutrino and described how the weak force operated. His theory explained how a neutron could transform into a proton while emitting an electron and a neutrino. It was elegant, mathematically precise, and turned out to be remarkably accurate. But it depended entirely on a particle that no one had ever directly observed. The challenge was stark. How do you detect a particle that barely interacts with anything? Pauli himself was deeply pessimistic. He reportedly bet a case of champagne that his particle would never be found. He later said he had committed a terrible thing by proposing a particle that could never be observed experimentally. And for a long time, it seemed like he might be right. The years stretched on. The 1930s passed. Fermi's theory gained acceptance because it explained beta decay so well, but the neutrino at its heart remained invisible. The 1940s came and went, a decade dominated by war and the development of nuclear weapons, work that deepened understanding of nuclear reactions, but brought physicists no closer to catching Pauli's ghost. The technology simply didn't exist. Detecting a particle with such an absurdly small interaction, probability required either an incredibly intense source of neutrinos or an incredibly massive detector, or both. In the 1930s and 40s, neither was available. By the early 1950s, the situation had changed. Nuclear reactors, developed as part of the Cold War nuclear programs, provided exactly the kind of intense neutrino source that was needed. A nuclear reactor is essentially a controlled chain reaction of uranium fission. Each fission event produces several neutron-rich fragments that undergo beta decay, and each beta decay produces a neutrino, or more precisely, an antineutrino. A large reactor produces an almost inconceivable number of these particles. The flux near a powerful reactor core reaches roughly 10 trillion antineutrinos per square centimeter per second. That's an enormous number of neutrinos concentrated in a relatively small area. If you could put a big enough detector close enough to a reactor, statistics might finally work in your favor. Even with a probability of interaction close to zero for any individual neutrino, the sheer torrent of particles might produce a few detectable events. Two American physicists saw this opportunity and seized it. Frederick Reines and Clyde Cowan designed an experiment to detect antineutrinos produced by the Savannah River nuclear reactor in South Carolina. Their approach relied on a process called inverse beta decay. On extremely rare occasions, an antineutrino would interact with a proton in a tank of water via the weak force, converting the proton into a neutron and producing a positron, the antimatter counterpart of the electron. The positron would immediately annihilate with a nearby electron, creating two gamma rays flying off in opposite directions. The neutron would bounce around briefly before being captured by a cadmium nucleus dissolved in the water, which would then emit its own distinctive gamma rays after a brief delay. These two bursts of gamma rays, separated by a tiny but measurable time gap of a few microseconds, created a unique signature, a double pulse of light with a specific timing pattern that could be distinguished from random background events. It was a masterpiece of experimental design. The double pulse signature was the key. Random background events could produce a single gamma ray easily enough, but producing two gamma ray bursts with exactly the right energies, separated by exactly the right time delay, was something that almost only a genuine anti-neutrino interaction could do. This gave Reines and Cowan a way to pick out the incredibly rare signal from the overwhelming background noise. Months of painstaking data collection followed. Background noise had to be carefully measured and subtracted. Every possible source of false signals had to be accounted for. They ran the experiment with the reactor on and with the reactor off. If the signal was really from reactor neutrinos, it should appear when the reactor was running and vanish when it was shut down. And that's exactly what they found. The signal was there, clear, consistent, and unmistakable. It appeared when the reactor was on and disappeared when the reactor was off. The ghost had been caught. Reines and Cowan sent a telegram to Wolfgang Pauli with a simple message. "We are happy to inform you that we have definitely detected neutrinos." Pauli was reportedly overjoyed. He shared the telegram with his colleagues at a conference in Zurich and drank the champagne he had wagered against this very outcome. The particle he had proposed out of desperation 26 years earlier, the particle he feared could never be found, had been observed. Energy conservation was saved. The desperate remedy had been real all along. Frederick Reines received the Nobel Prize in Physics in 1995 for this discovery. Clyde Cowan had died in 1974 and could not share the honor, as the Nobel Prize is not awarded posthumously. So, what exactly is a neutrino? Let's establish this precisely, because it matters for everything that follows. A neutrino is a fundamental particle, meaning it is not made of anything smaller as far as we know. It's not composed of quarks like protons and neutrons. It's not a composite structure, it's elementary, indivisible, a basic building block of reality. A neutrino belongs to a family of particles called leptons. There are 6 leptons in total, arranged in 3 pairs called generations. The first generation contains the electron and the electron neutrino. The second contains the muon, a heavier cousin of the electron, and the muon neutrino. The third contains the tau particle, heavier still, and the tau neutrino. These 3 types, electron neutrino, muon neutrino, and tau neutrino, are called the 3 flavors of neutrinos. Each one is associated with its corresponding charged lepton. For decades after Pauli's proposal, physicists assumed neutrinos were completely massless. The original standard model of particle physics, the mathematical framework that describes all known fundamental particles and their interactions, assigned neutrinos 0 mass. This seemed reasonable. No experiment had ever measured a neutrino mass, and the theory worked perfectly well without one. But as we'll discover later in this story, that assumption turned out to be wrong. Neutrinos do have mass, but it's so unimaginably small that we still haven't pinned down the exact value. The best current limits suggest the combined mass of all 3 neutrino flavors is less than about 1/10 of an electron volt. The electron, the lightest commonly discussed particle, has a mass of about 511,000 electron volts. That means neutrinos are at minimum several million times lighter than an electron. They are the lightest known massive particles in the universe. Neutrinos carry no electric charge and no color charge. We've already seen what this means. The electromagnetic force and the strong nuclear force, the two forces that govern almost everything about how matter behaves, simply have no hold on them. But it's worth pausing on just how total this exclusion is. A neutrino cannot emit or absorb a photon. It cannot interact with an electric field or a magnetic field. It is completely invisible to every detector that relies on electromagnetic interactions, which is essentially every detector humans have ever built for any purpose. It cannot feel the force that holds nuclei together. The only door left open to it is the weak nuclear force, a force mediated by carrier particles so heavy that its effective range barely extends beyond the boundaries of a single nucleon. A neutrino moves through the universe, interacting only through the weakest relevant force over the shortest relevant distance. It simply lacks the properties that would allow the universe's other forces to take hold of it. The neutrino is one of the strangest objects in all of physics. Not because it behaves strangely, it obeys every known law with perfect fidelity, but because its properties place it at the extreme edge of the physical landscape. It is the lightest massive particle. It is the most weakly interacting of all known matter particles. And by sheer numbers, it is the most abundant. For every atom that exists in the cosmos, there are roughly 1 billion neutrinos streaming from every star, every nuclear reaction, every echo of the Big Bang. The universe is saturated with them, and the universe barely notices. What we need to understand next is why this ghostly behavior follows so naturally from the physics of forces and probabilities. Because the neutrino's ability to pass through virtually anything isn't mysterious once you understand the mathematics behind it. It's inevitable. And the numbers, when you work them out, are among the most astonishing in all of science. To understand why neutrinos pass through matter as if it weren't there, you first need to understand what it actually means for two particles to interact. Because at the subatomic level, interaction doesn't work the way you might imagine. Two particles don't bump into each other like billiard balls. They don't have hard surfaces that collide. There are no tiny solid spheres crashing together in some microscopic game of pool. Instead, an interaction happens when two particles come close enough for one of the fundamental forces to mediate an exchange between them. The force reaches out across a certain distance, the particles influence each other, and something happens. A deflection, a transformation, an exchange of energy. The key phrase is close enough. And how close is close enough depends entirely on which force is doing the work. Physicists quantify this using a concept called a cross-section. Now, despite the name, this isn't literally the cross-sectional area of a particle the way you might measure the area of a circle. It's more subtle than that. A cross-section is the effective target area that a particle presents for a particular type of interaction. Think of it this way. Imagine you're throwing tennis balls at a barn door. The door is large, so your chances of hitting it are high. The door has a large cross-section for tennis ball interactions. Now imagine instead that you're throwing tennis balls at a needle standing upright in the middle of an open field. The needle is tiny, so your chances of hitting it are almost zero. The needle has a minuscule cross-section for tennis ball interactions. Both objects are real. Both are physically there. But the probability of your tennis ball making contact is vastly different, because the effective target area is vastly different. In particle physics, cross-section is measured in units of area, typically square centimeters, or a unit called the barn, which is 10 to the negative 24 square centimeters. That might sound small, and it is by everyday standards, but it's actually quite large by particle physics standards. A barn is roughly the cross-sectional area of a uranium nucleus. Physicists named it during the Manhattan Project because compared to the tiny targets they were used to dealing with, a uranium nucleus seemed as big as a barn. The humor was intentional. Particle physicists have a dry sense of comedy when it comes to naming things. For electromagnetic interactions, cross-sections are relatively substantial. When a photon encounters an atom, the effective target area is generous because the electromagnetic force has infinite range, and the electron cloud occupies a region much larger than the nucleus. The photon has a high probability of being absorbed, scattered, or otherwise interacting. This is why most solid materials are opaque. Visible light gets absorbed within the first few micrometers of most solid surfaces. Even X-rays, which are far more penetrating, typically get absorbed within a few centimeters of dense material like lead. Electromagnetic interactions are common, frequent, and efficient. They happen all the time, everywhere, constantly. Your entire sensory experience of reality is built on the fact that electromagnetic interactions happen easily and often. For the strong nuclear force, cross-sections are also respectable, but only at extremely short range. If a particle that feels the strong force, a proton, a neutron, or any other particle containing quarks, gets within about 10 to the negative 15 meters of another such particle, the strong force will seize hold with tremendous power. That range is essentially the diameter of a nucleus. Within that tiny sphere, the strong force dominates everything, but outside that sphere, it vanishes. So the strong force cross-section is roughly the size of the nucleus itself, about 10 to the negative 26 square centimeters. Anything that can get close enough to a nucleus will interact strongly, but getting close enough is the challenge, because the nucleus is incredibly small compared to the atom. Now we arrive at the weak nuclear force, and this is where the numbers become almost absurd. The cross-section for a typical weak interaction involving a neutrino is approximately 10 to the negative 44 square centimeters. Let me try to convey how small that is. If you were to write this number as a decimal, you would write a 0, then a decimal point, then 43 more zeros, and only then would you write the first non-zero digit. Compare this to the strong force cross-section of 10 to the negative 26 square centimeters. The weak interaction cross-section is roughly 10 to the 18th times smaller. That's a factor of a billion billion. A billion times smaller than a target that's already the size of an atomic nucleus. Why is the weak force cross-section so catastrophically small? The answer lies in the particles that carry the force. Every fundamental force is transmitted by carrier particles, also called gauge bosons. These carriers are what actually mediate the interaction between two particles. For electromagnetism, the carrier is the photon. Photons are massless, and this is why the electromagnetic force has infinite range. A massless carrier can exist for as long as it needs to, and travel as far as it needs to. There's no energy cost to creating a virtual photon that mediates an electromagnetic interaction, regardless of distance. This is why two magnets can attract or repel each other from across a room, and why the sun's gravity, mediated by the hypothetical graviton, reaches all the way to Neptune and beyond. For the strong force, the carriers are gluons. Gluons are also massless in principle, but the strong force has a peculiar property called confinement that restricts its effective range to nuclear distances. The details are complex, involving the self-interaction of gluons, but the practical result is that the strong force is confined to regions the size of a nucleus. For the weak nuclear force, the carriers are 3 particles: the W plus boson, the W minus boson, and the Z boson. And here is the critical difference. These bosons are not massless. They are enormously heavy. The W bosons have a mass of about 80.4 gigaelectronvolts each, and the Z boson has a mass of about 91.2 gigaelectronvolts. To put that in perspective, a proton has a mass of about 0.938 gigaelectronvolts. The W and Z bosons are roughly 80 to 90 times heavier than a proton. They are among the heaviest elementary particles ever discovered. The mass of the carrier particle directly determines the range of the force it mediates. This isn't a rough rule of thumb. It's a precise consequence of quantum mechanics, specifically the Heisenberg uncertainty principle. The uncertainty principle tells us that nature allows brief violations of energy conservation, but only for extremely short periods of time. A virtual particle can borrow energy from the vacuum to pop into existence, but the more energy it borrows, that is, the more massive the virtual particle, the less time it's allowed to exist before it must be reabsorbed. Since even a virtual particle can't travel faster than the speed of light, a shorter existence means a shorter distance traveled, which means a shorter range for the force. For the massless photon, the borrowed energy is essentially 0. The allowed time is essentially infinite, and the range is infinite. For the W and Z bosons, the borrowed energy is enormous, roughly 80 to 90 times a proton's mass worth of energy, and the allowed time is fantastically brief. When you work out the numbers, you get exactly the range. We encountered earlier about 10 to the negative 18 meters, 1 atometer, 1 quintillionth of a meter. But now we understand why the range is so short. It's not an arbitrary fact. It's a direct, unavoidable consequence of the W and Z bosons being so heavy. The heavier the carrier, the shorter its borrowed existence, the shorter the range. The enormous mass of the weak force carriers is the reason the weak force barely reaches beyond the boundaries of a single nucleon. Let that settle for a moment. A proton is already incomprehensibly small. You could line up roughly 40 billion protons across the width of a single human hair. And the weak force operates over a distance 1,000 times smaller than that. For a neutrino to interact with another particle through the weak force, the neutrino must pass within about 10 to the negative 18 meters of that particle. It essentially has to score a direct hit on a target that is 1,000 times smaller than the nucleus of an atom, and the nucleus itself is already 100,000 times smaller than the atom. Now, think about what a neutrino encounters when it enters a block of matter. Let's say it's flying through your body, or through a wall, or through the entire planet Earth. It encounters vast numbers of atoms. Your body alone contains roughly 7 billion atoms, but each of those atoms is overwhelmingly empty space. The nucleus sits at the center, occupying a volume that is about 1 quadrillionth of the atom's total volume. And the weak force target within that nucleus, the region where the neutrino would need to pass to have any chance of interacting, is 1,000 times smaller still. The neutrino flies through atom after atom after atom, passing through the cavernous empty space within each one. Even when it passes close to a nucleus, close isn't close enough. It needs to pass within 10 to the negative 18 meters of a quark or other weak force sensitive particle, and the probability of that happening on any given encounter is almost vanishingly small. Let's put specific numbers on this. The interaction cross-section for a solar neutrino, one with an energy of a few million electron volts, interacting with a nucleon is approximately 10 to the negative 44 square centimeters. The number of nucleons in a cubic centimeter of water is about 6.7 times 10 to the 23. If you multiply the cross-section by the number density of targets and by the distance the neutrino travels, you get the probability of interaction. For a neutrino passing through the entire Earth, a distance of about 12,700 kilometers through rock and iron with an average density much higher than water, the probability of interacting is still only about 1 in 10 billion. One single neutrino flying through the entire diameter of a planet made of rock and metal, and there's only about a 1 in 10 billion chance that it will interact with even a single atom along the way. This leads to one of the most striking thought experiments in all of physics. Imagine constructing a wall of solid lead. Not an ordinary wall. A wall that extends for 1 light year. 1 light year of solid lead, roughly 9.46 trillion kilometers. Atom after atom after atom packed together in a continuous barrier of one of the densest elements on Earth. If you fired a beam of neutrinos at this wall, neutrinos with energies typical of those produced by the sun, approximately half of them would pass through the other side completely unscathed. Half. A light year of solid lead, and it only manages to stop roughly half the neutrinos. The other half emerge from 9.46 trillion kilometers of solid matter, as if nothing happened. As if the wall weren't there at all. This is not magic. This is not a violation of physics. This is pure probability. The laws of physics absolutely permit a neutrino to interact with a lead atom through the weak force. It happens. We measure it in our detectors every day. But the probability of any single neutrino interacting with any single atom is so unfathomably low that even stacking up atoms for a light year doesn't guarantee an interaction. The universe built a particle whose interaction probability is so small that practically infinite amounts of matter are functionally transparent to it. Now consider what this means for the neutrinos surrounding you at this very moment. The Sun is a thermonuclear furnace of almost incomprehensible scale, deep in its core, where the temperature reaches about 15 million degrees Celsius, and the pressure is roughly 265 billion times the atmospheric pressure on Earth's surface. Hydrogen nuclei are being fused together into helium. This process, called the proton-proton chain, releases energy in the form of photons and kinetic energy, but it also produces neutrinos, specifically electron. Neutrinos. Every time certain fusion reactions occur, and they occur constantly, trillions upon trillions of times every second, neutrinos are emitted as a byproduct. The Sun generates roughly 2 times 10 to the 38th neutrinos every second. That's 200 billion neutrinos pouring out of the Sun's core every single second, streaming outward in all directions at very nearly the speed of light. By the time these neutrinos reach Earth, about 8 minutes and 20 seconds later, they've spread out over an enormous sphere with a radius of 150 million kilometers. But even spread out across this vast distance, the flux at Earth is staggering. About 65 billion solar neutrinos pass through every single square centimeter of area facing the Sun, every single second. Hold up your thumbnail. That's roughly 1 square centimeter. 65 billion neutrinos just flew through it, and they didn't stop when they entered your thumbnail. They continued straight through your hand, through your arm, through your torso, through the chair you're sitting in, through the floor, through the foundation of the building, through the bedrock below, through the mantle, through the liquid iron outer core, through the solid iron inner core, through the mantle on the other side, through the crust, through the ocean or land surface on the far side of the planet, and out into space again, without slowing down, without being deflected, without interacting with a single atom in the entire 12,700 kilometer journey through the body of a planet. During the day, these neutrinos arrive from above, from the direction of the sun. At night, they come from below. They've already passed through the entire Earth to reach you. Day and night, unceasing, you are bathed in a continuous flood of neutrinos that you will never feel. They have been passing through you since the moment you were born. They passed through the hospital where you were born. They passed through every building, every mountain, every ocean. They passed through the moon. They passed through Jupiter. Nothing in the solar system presents a meaningful obstacle to them. And solar neutrinos are just one source. The universe produces neutrinos in many different ways, and they're coming at you from every direction simultaneously. Cosmic rays, high-energy protons and other nuclei that originate from supernovae, active galactic nuclei, and other violent astrophysical events constantly bombard Earth's atmosphere. When these fast-moving particles slam into nitrogen and oxygen molecules in the upper atmosphere at altitudes of roughly 15 to 35 kilometers, they create cascading showers of secondary particles. Among these are pions and coans, unstable particles that quickly decay, and many of their decay products include neutrinos. These atmospheric neutrinos rain down on Earth continuously from every direction in the sky. Some travel downward through just a few kilometers of atmosphere to reach detectors on the surface. Others are produced on the far side of the planet, pass through the entire Earth, and arrive from below. The flux of atmospheric neutrinos is much lower than the solar neutrino flux, but they tend to have higher energies, which makes them scientifically interesting for different reasons. Nuclear power plants are another source. A typical nuclear reactor produces roughly 5 times 10 to the 20 antineutrinos per second through the beta decays of fission products in the reactor core. There are about 440 nuclear reactors operating worldwide, and their combined neutrino output contributes to the background flux that permeates the planet. These reactor neutrinos have been crucial for studying neutrino properties because, unlike solar or atmospheric neutrinos, their source location, intensity, and energy spectrum are precisely known and controllable. The Earth itself is a neutrino source. Radioactive elements embedded in the planet's crust and mantle, potassium-40, uranium-238, thorium-232, and their various decay products, undergo beta decay continuously. Each decay releases an antineutrino. These geoneutrinos, as they're called, stream outward from the rocks beneath your feet. Detecting them has given physicists an entirely new way to study the composition and thermal dynamics of Earth's interior, complementing seismology and other geological methods. The total geoneutrino flux is modest compared to solar neutrinos, but it's a measurable signal that carries information about our planet's radioactive heat engine. Then there are neutrinos from supernovae. when a massive star reaches the end of its life and its core collapses. The resulting explosion releases an almost unimaginable torrent of neutrinos. In fact, roughly 99% of the total energy released in a core collapse, supernova, about 3 times 10 to the 46 joules, is carried away by neutrinos. Only about 1% goes into the visible light, the shock wave, and the kinetic energy of the debris that we observe as the supernova explosion. The neutrino burst from a nearby supernova is so intense that even with their absurdly small interaction cross-sections, modern detectors can catch dozens of them. This was demonstrated spectacularly in 1987, a story we'll return to soon. Beyond all of these individual sources, there are neutrinos from the most extreme environments in the cosmos. The regions around supermassive black holes at the centers of distant galaxies. The relativistic jets of blazars that shoot beams of matter and energy across millions of light years. And the collisions of neutron stars. These astrophysical neutrinos carry energies millions or billions of times higher than solar neutrinos, and detecting them has opened an entirely new branch of astronomy. Higher energy neutrinos have larger interaction cross-sections. The probability of interaction grows with energy, which means detectors have a somewhat better chance of catching them. But even at the highest energies ever observed, neutrinos remain staggeringly more penetrating than any other known particle. And finally, perhaps most remarkably of all, there are neutrinos left over from the Big Bang itself. In the first second after the origin of the universe, when temperatures exceeded 10 billion degrees and the entire cosmos was a dense soup of particles and radiation, neutrinos were being produced and annihilated in enormous numbers, interacting freely with everything around them. But as the universe expanded and cooled, about 1 second after the Big Bang, the neutrinos decoupled, they stopped interacting, and have been streaming freely through the universe ever since. For 13.8 billion years, these primordial neutrinos have been drifting through space, cooling as the universe expanded, their energies dropping to incredibly low values. They form what's called the cosmic neutrino background, a relic of the universe's first second. They are all around you right now. They are among the oldest particles in existence. And we'll return to them later because what they might tell us about the birth of the universe is extraordinary. When you add all these sources together, the sun, the atmosphere, nuclear reactors, radioactive rocks, supernovae past and present, astrophysical jets, and the primordial background, the universe is absolutely saturated with neutrinos. The cumulative picture is overwhelming. Every source, solar, atmospheric, terrestrial, reactor, astrophysical, primordial, contributes to a universe drenched in neutrinos. They fill every cubic centimeter of space, they pass through every planet, every star, every galaxy, and essentially none of them interact with anything. There's a beautiful illustration of the contrast between neutrinos and photons that makes the whole picture vivid. Consider a photon and a neutrino produced side by side in the same nuclear fusion reaction at the center of the sun. They're born at the same moment, in the same place, from the same event. The neutrino, interacting only through the weak force, flies straight outward through the sun's interior. It passes through roughly 700,000 kilometers of incredibly dense stellar plasma. Matter so compressed that the core density is about 150 times the density of water. Without interacting, it exits the sun about 2 seconds after being created. It then crosses the 150 million kilometer gulf between the Sun and Earth in about 8 minutes and 18 seconds. Total travel time from creation to your eyeball, about 8 minutes and 20 seconds. The photon has a very different journey. It interacts electromagnetically, which means it's constantly being absorbed and re-emitted by the charged particles in the Sun's interior. It bounces from atom to atom, scattering in random directions, taking a tortuous random walk outward through the solar interior. On average, a photon scatters after traveling only about 1 centimeter before it's absorbed and re-emitted by another atom. 1 centimeter at a time, in a random direction each time, across 700,000 kilometers of solar material. The result is that the average photon takes an estimated 170,000 years to random walk from the core to the surface. 170,000 years for the photon. 2 seconds for the neutrino. Same starting point, same solar material, but the photon interacts electromagnetically, and the matter is opaque to it. The neutrino interacts only through the weak force, and the same matter is perfectly transparent. This contrast captures everything. The electromagnetic force makes matter opaque to photons. The strong force makes nuclear material opaque to hadrons. But the weak force, with its absurdly short range and its enormously heavy carrier particles, makes the interaction probability so small that matter is essentially invisible to neutrinos. A neutrino can fly through a star in seconds. It can fly through a planet without noticing. It can fly through a light year of solid lead and have a coin flip chance of emerging from the other side. The neutrino is not breaking any law of physics. It's not cheating. It's not doing anything the equations say it shouldn't. The equations tell us precisely this, that a particle with no electric charge, no color charge, and negligible mass, interacting only through a force with a range of 10 to the negative 18 meters mediated by carriers weighing 80 to 90 proton masses, will have an interaction cross-section so small that the entire material universe is functionally transparent to it. The ghost isn't supernatural. The ghost is exactly what the physics predicts, and yet we've caught it. We've detected this particle that passes through planets and stars and light years of lead. We've measured its properties, we've counted its flavors, we've tracked its oscillations, we've used it to peer inside the hearts of stars and to look back to the first second of the universe. The story of how we did that, how humans managed to observe the nearly unobservable, is one of the most remarkable chapters in the history of science, and it begins with a tank of cleaning fluid buried deep inside a gold mine. Given everything we've established, that neutrinos barely interact with anything, that they fly through planets and stars and light years of solid lead as if those objects were empty space, you might think detecting them would be impossible, and for decades, many physicists thought exactly that. Pauli himself doubted it would ever happen. The challenge is staggering on its face. You're trying to observe a particle whose single defining characteristic is that it almost never does anything observable. It's like trying to photograph a shadow that only appears once every billion years. The odds are against you in the most extreme way imaginable. But physicists are stubborn people, and they are creative people. And over the course of the 20th century, they figured out something important. While any individual neutrino is overwhelmingly unlikely to interact with any individual atom, if you gather enough neutrinos and enough target atoms in one place and wait long enough, the occasional interaction becomes statistically inevitable. It's a matter of scale. Imagine you have a coin that lands on heads once in every 10 billion flips. If you flip it once, you'll get tails. If you flip it 1,000 times, you'll still get tails every time. 1,000,000 times, still tails. But if you flip it 10 billion times, you'll probably see heads once. Neutrino detection works on this exact principle. You expose enormous quantities of target material, hundreds or thousands of tons of atoms, to enormous fluxes of neutrinos, and you wait patiently for the incredibly rare interaction that statistics guarantee must eventually occur. But there's an enormous complication. The world is full of other particles that can mimic the signal you're looking for. Cosmic rays constantly bombard Earth's surface, producing showers of muons, electrons, gamma rays, and other particles. Radioactive elements in surrounding rock emit radiation continuously. Stray particles from 1,000 different sources can enter your detector and produce signals that look exactly like a neutrino interaction. If you put your detector on the surface of the Earth, these background events will overwhelm the faint neutrino signal by a factor of millions or billions. You'll never see the needle in that haystack. So physicists do something dramatic. They go underground, deep underground, hundreds or thousands of meters below the Earth's surface, where layers of rock act as a natural shield, blocking nearly all cosmic rays and other stray particles. Rock is excellent at stopping electromagnetically and strongly interacting particles. Muons, the most penetrating component of cosmic ray showers, are gradually absorbed as they pass through rock, losing energy with each electromagnetic interaction. Go deep enough, and even the muon flux drops to almost nothing. The only particles that can still reach your detector in significant numbers at these depths are neutrinos, because neutrinos pass through rock just as easily as they pass through everything else. Deep underground, you've created an environment where almost the only thing that can trigger your detector is the very thing you're looking for. The first person to successfully exploit this strategy for solar neutrinos was Raymond Davis Jr., an American chemist and physicist with an extraordinary talent for precision measurement and an almost superhuman patience. In the mid-1960s, Davis constructed an experiment deep inside the Homestake gold mine in Lead, South Dakota, about 1,470 meters underground. The mine had been in operation since the 1800s, its tunnels bored deep into the Black Hills of South Dakota in search of gold. Davis wasn't looking for gold. He was looking for something far more elusive, evidence that neutrinos from the sun's core were reaching Earth, and occasionally, against all odds, interacting with matter. The heart of his experiment was a tank containing roughly 615 metric tons of perchloroethylene, ordinary industrial dry cleaning fluid. This is not what you might picture when you think of a cutting-edge physics experiment. There were no gleaming instruments, no blinking panels of electronics. It was essentially a very large cylindrical vat of solvent sitting in a cavern carved out of rock, connected to some pumping equipment and chemical extraction apparatus. It was unglamorous to the point of being almost absurd. Visitors to the mine who saw it for the first time were sometimes baffled. This was supposed to detect particles from the sun? A tank of cleaning fluid in a hole in the ground? But its design was brilliant. The choice of material was not arbitrary. It was the product of careful theoretical calculation about which nuclei would be most sensitive to the particular energies of solar neutrinos. Perchloroethylene contains chlorine, and specifically the isotope chlorine-37. which makes up about 1/4 of all natural chlorine. On extraordinarily rare occasions, a solar neutrino would interact with a chlorine-37 nucleus through the weak force, transforming it into an argon-37 nucleus and emitting an electron. This reaction, called the inverse beta decay of chlorine-37, was the detection mechanism. Each time it occurred, one atom of chlorine-37 would become one atom of argon-37. Davis's job was to count the argon atoms. Pause and consider the absurdity of this task. He had 615 metric tons of fluid. That's roughly 2,380,000 litres. In this enormous volume, the sun's neutrino flux was predicted to produce, on average, roughly 1 or 2 argon-37 atoms every single day. 1 or 2 atoms per day in 615 tons of liquid. It would be like trying to find one specific grain of sand that had been secretly added to a swimming pool full of sand. Except the grain is an atom and the swimming pool is the size of a small building. Finding it required chemical techniques of extraordinary sensitivity, the kind of work that demanded not just scientific knowledge, but something closer to artistry. Davis had to extract individual atoms from a sea of trillions of trillions. Davis ran the experiment in cycles lasting several weeks. He would let the detector sit undisturbed, quietly, accumulating argon atoms from the rare neutrino interactions. Then he would flush helium gas through the entire tank, which would carry the tiny number of volatile argon atoms out of the liquid. He'd collect the helium, extract the argon through painstaking chemical separation, and place the argon sample in a small proportional counter, a device that could detect the radioactive decay of individual argon-37 atoms as they converted back to chlorine-37. By counting these decays over a period of months, he could determine how many neutrino interactions had occurred during the exposure period. Each complete measurement cycle, from closing the tank to flushing it, extracting the argon, purifying it, and counting the decays, took the better part of a year. The statistical uncertainties were large because the numbers were so small. A handful of atoms here, a handful there. Davis needed many cycles, many years of data to build up enough statistics to say anything definitive. He ran the experiment for nearly 3 decades. 3 decades of cycling the same tank, flushing the same helium, extracting the same infinitesimal quantities of argon, counting the same faint radioactive decays. It was science at its most patient and most demanding. Davis spent more time with that tank of cleaning fluid than most people spend in any single career. He began the experiment as a middle-aged scientist and was still running it as an elderly man. And then the results came in. And they were puzzling. Davis did find argon atoms, definitive proof that solar neutrinos were reaching his detector and occasionally interacting. The experiment worked. The neutrino, Pauli's ghost particle, was being caught in a vat of dry cleaning solvent a mile underground. But Davis found only about 1/3 as many argon atoms as theorists had predicted. Solar models, built on our understanding of nuclear fusion in the sun's core, predicted a certain rate of neutrino interactions based on the temperature, density, and composition of the solar interior. Davis was measuring roughly 1/3 of that predicted rate. 2/3 of the expected neutrinos appeared to be missing. This discrepancy became known as the solar neutrino problem, and it was one of the most stubborn and perplexing puzzles in physics for the next 30 years. It gnawed at the field. It divided physicists into camps. It spawned hundreds of theoretical papers, dozens of proposed explanations, and years of heated debate at conferences around the world. Because the discrepancy struck at something fundamental. Either we didn't understand how the sun works, which would mean our models of stellar physics were deeply flawed, or we didn't understand neutrinos, which would mean our standard model of particle physics was incomplete. Both possibilities were deeply uncomfortable. Both had enormous consequences. The stakes were high because the solar model wasn't just some rough sketch. It was one of the most carefully constructed and thoroughly tested models in all of astrophysics. Decades of work had gone into understanding stellar interiors. The temperatures, pressures, densities, energy transport mechanisms, nuclear reaction rates, and compositions. The solar model successfully predicted the sun's luminosity, its radius, its surface temperature, and the frequencies of its oscillation modes, which had been measured with extraordinary precision by helioseismology. It was not a model that seemed likely to be wrong by a factor of 3. And yet, Davis kept getting the same answer. Year after year, cycle after cycle, he extracted his argon atoms and counted them. And the number was always about 1/3 of what the theorists said it should be. Some physicists questioned his methods. Some wondered if his chemical extraction was inefficient, if he was losing argon atoms during the process, and undercounting. Davis tested this by injecting known quantities of argon into his tank and extracting them. He consistently recovered more than 90%. The extraction was working. The deficit was real. Other physicists scrutinized the solar models. Maybe the core temperature was slightly lower than calculated. A small change in temperature could significantly affect the rate of certain fusion reactions and thus the neutrino production rate. Solar physicists examined this possibility meticulously, adjusting parameters, refining their inputs, testing sensitivity to various assumptions. The models were robust. You could tweak parameters within their allowed ranges and reduce the predicted neutrino rate somewhat, but not by a factor of 3. The discrepancy persisted stubbornly, no matter how you adjusted the model within reasonable bounds. The solar neutrino problem became a slow-burning crisis. Not an explosive controversy, but a persistent, nagging wound in the body of physics that wouldn't heal. For 30 years, it sat there, defying resolution. Davis kept running. His experiment. Theorists kept arguing. And the missing neutrinos refused to be found. There were several possible explanations, and physicists debated them vigorously. Maybe the nuclear physics inputs were wrong. Perhaps the cross-sections of certain nuclear reactions in the sun had been measured incorrectly in laboratory experiments. Physicists revisited these measurements, improving their precision with better accelerators and better detectors. The results tightened the predictions somewhat but didn't resolve the discrepancy. Or maybe, and this was the most radical and exciting possibility, something was happening to the neutrinos themselves during their 8-minute journey from the sun to Earth. Maybe they were changing, transforming, becoming something that Davis's detector couldn't see. Here's the key. Davis's chlorine detector was only sensitive to electron neutrinos. That's the flavor produced in the sun's fusion reactions. If some of those electron neutrinos were transforming into muon neutrinos or tau neutrinos during their journey from the sun to Earth, they would still arrive at the home state mine. They would still pass through the tank of perchloroethylene, but they would be invisible to the chlorine-37 reaction, which only responds to electron neutrinos. They'd be there, but Davis couldn't see them. This idea that neutrinos could spontaneously change from one flavor to another during flight is called neutrino oscillation. It was first proposed in the late 1950s by the Italian-Russian physicist Bruno Pontecorvo. According to quantum mechanics, if the three neutrino flavors have slightly different masses, then something strange happens. A neutrino produced as a pure electron neutrino is actually a quantum superposition of three mass states. As the neutrino travels through space, these mass states evolve at slightly different rates because they have slightly different masses. The result is that the probability of the neutrino being detected as an electron neutrino varies with distance. It oscillates. At some distances, the neutrino is mostly electron flavor. At other distances, it's mostly muon or tau. It's a purely quantum mechanical effect, a consequence of the wave nature of matter, and it has no analogy in everyday experience. But for neutrino oscillation to work, neutrinos must have mass. If all three flavors were massless, as the standard model of particle physics had originally assumed, the mass states would all be identical. There would be no differential evolution, and no oscillation would occur. The fact that Davis was seeing fewer electron neutrinos than expected was a tantalizing hint that neutrinos might not be massless after all. But a hint is not proof. It took decades and two entirely different experiments on opposite sides of the Pacific Ocean to provide definitive evidence. The first breakthrough came from Super Kamiokande, a colossal detector located in the Mozumi mine, about 250 kilometers northwest of Tokyo, in the mountains of Gifu Prefecture, Japan, beneath Mount Ikeno. Super Kamiokande began operations in 1996, and it represented a dramatic leap in scale and sensitivity compared to anything that had come before. The detector is a cylindrical stainless steel tank, about 40 meters in diameter and 40 meters tall, filled with 50,000 metric tons of ultra-pure water. The water is so pure that it has been filtered to remove virtually every trace of dissolved minerals and contaminants, because even tiny impurities can produce spurious light signals that would mask the faint neutrino events. Surrounding the water on all sides are 11,180 photomultiplier tubes. Extraordinarily sensitive light detectors, each about 50 centimeters in diameter, mounted on the inner walls of the tank. These photomultiplier tubes are so sensitive that they can detect a single photon of light. They stare inward at the water from every direction, watching, waiting for the faintest flash. The detection principle relies on a phenomenon called Cherenkov radiation. When a charged particle travels through water faster than the speed of light in water, which is about 75% of the speed of light in vacuum, it creates a cone of faint blue light. This is the optical equivalent of a sonic boom. A jet traveling faster than the speed of sound in air creates a shockwave, a cone of compressed air that we hear as a thunderous boom. Similarly, a particle traveling faster than the local speed of light in a transparent medium creates a shockwave of light, a cone of photons spreading out behind it. No law of physics is violated. Nothing is exceeding the speed of light in a vacuum. But light travels slower in water than in vacuum, and a high-energy charged particle can exceed that reduced speed. When a neutrino interacts with a water molecule through the weak force, an event that happens only a handful of times per day, even in 50,000 tons of water, it can produce a charged particle either an electron or a muon, depending on the neutrino's flavor. If that charged particle is fast enough, it emits a cone of Cherenkov light. The photomultiplier tubes detect this faint ring of light, and from the pattern, the shape of the ring, its brightness, its position on the detector walls, physicists can reconstruct the direction the neutrino came from, its energy, and its flavor. In 1998, a team led by Takaaki Kajita at Super Kamiokande announced one of the most important discoveries in the history of particle physics. They had been studying atmospheric neutrinos. Neutrinos produced when cosmic rays from deep space strike atoms in Earth's upper atmosphere. These cosmic ray collisions create showers of secondary particles, including pions, which decay into muons and muon neutrinos. Some of these atmospheric muon neutrinos travel a short distance downward through the atmosphere to reach the detector, a journey of roughly 15 to 35 kilometers. Others are produced on the far side of the planet, travel downward through the atmosphere there, then pass through the entire Earth, a journey of up to roughly 12,700 kilometers, and arrive at the detector from below. If neutrinos don't oscillate, both groups should arrive in equal numbers. The production rate is essentially the same in all directions. The neutrinos coming from below travel a longer distance through the Earth, but neutrinos pass through the Earth without difficulty, so that shouldn't matter. Both groups should look the same, but they didn't. Kajita's team found a striking asymmetry. The number of muon neutrinos arriving from below, after traveling through the Earth, was significantly less than the number arriving from above. The downward traveling neutrinos, which had only traveled a few dozen kilometers, arrived at nearly the expected rate. The upward traveling neutrinos, which had traveled thousands of kilometers, showed a clear deficit. The farther the neutrinos had traveled, the more of them had disappeared. The explanation was neutrino oscillation. The muon neutrinos that traveled the longer distance through the Earth had more time to oscillate into tau neutrinos, which Super Kamiokande's detection method could not easily identify. The muon neutrinos that traveled only a short distance didn't have enough time to oscillate significantly, so they arrived as muon neutrinos and were detected normally. The deficit depended on distance in exactly the way oscillation theory predicted. This was direct, powerful evidence that neutrinos change flavor as they travel through space. And because flavor oscillation requires different masses for different flavors, it meant neutrinos have mass. The second breakthrough came from the Sudbury Neutrino Observatory, known as SNO, located about 2,000 meters underground in an active nickel mine near Sudbury, Ontario, Canada. SNO was led by Arthur MacDonald and was designed specifically to settle the solar neutrino problem once and for all. Its design was ingenious because it could do something no previous detector could: detect all three flavors of neutrinos, not just electron neutrinos. SNO's advantage came from its detection medium. Instead of ordinary water, the heart of the detector contained 1,000 metric tons of heavy water. Water in which the ordinary hydrogen atoms are replaced by deuterium, a heavier isotope of hydrogen whose nucleus contains 1 proton and 1 neutron. This heavy water was borrowed from Canada's nuclear industry. It was extraordinarily valuable, worth roughly 300 million Canadian dollars, and was kept in an acrylic vessel surrounded by ordinary water and monitored by about 9,600 photomultiplier tubes. Heavy water gave SNO access to 3 different neutrino interaction channels, each with different sensitivities. The first was the charged current reaction. In this process, an electron neutrino interacts with the deuterium nucleus and transforms it into 2 protons plus an electron. This reaction is sensitive only to electron neutrinos. The second was the neutral current reaction. In this process, a neutrino of any flavor, electron, muon, or tau, interacts with a deuterium nucleus and breaks it apart into a free proton and a free neutron. The neutrino bounces off and continues on its way, and the free neutron is eventually captured, producing a detectable gamma ray. This reaction is equally sensitive to all 3 flavors. The third was elastic scattering, where a neutrino bounces off an electron, which is sensitive to all flavors but predominantly to electron neutrinos. The logic was devastatingly simple. If the solar neutrino problem was caused by incorrect solar models, if the sun really was producing fewer neutrinos than predicted, then both the charged current measurement and the neutral current measurement would show a deficit. Fewer total neutrinos means fewer of every type. But if the problem was caused by neutrino oscillation, if electron neutrinos were changing into muon and tau neutrinos during their journey, then the charged current measurement would show a deficit, because it only sees electron neutrinos, and some of them have transformed. But the neutral current measurement would show the full expected rate, because it counts all flavors equally and the total number of neutrinos hasn't changed. They've just changed costume. The results, published in 2001 and refined over the following years, were unambiguous. The charged current measurement found only about 34% of the expected electron neutrinos, consistent with what Raymond Davis had been seeing for 30 years in the Homestake mine. But the neutral current measurement found the full expected number of total neutrinos. The numbers match the solar model predictions beautifully. Every neutrino the sun was predicted to produce was accounted for. None were missing. The deficit was entirely explained by flavor transformation. The solar neutrino problem, which had haunted physics for 3 decades, was solved, and the resolution was beautiful in its completeness. The sun was working exactly as models predicted. The nuclear physics was correct. Davis's experiment was correct. Everyone had been right all along, except for the assumption that neutrinos were massless and couldn't change flavor. The neutrinos were all there, every single one the sun had produced. They had simply changed flavor on the way to Earth, converting from electron neutrinos, the only type Davis could detect, into muon and tau neutrinos that his chlorine experiment was blind to. And this oscillation proved that neutrinos have mass, because massless particles cannot oscillate between flavors. Raymond Davis, who had spent 30 years being told his results were wrong, was vindicated. The data had been right from the beginning. It was our assumptions about neutrinos that needed updating. The Nobel Prize in Physics for 2002 was awarded jointly to Raymond Davis Jr. for his decades of solar neutrino detection, and to Masatoshi Koshiba, who built the Kamiokande detector in Japan, a predecessor to Super Kamiokande that had confirmed the solar neutrino deficit using a completely different detection method. The 2015 Nobel Prize in Physics went to Takaaki Kajita of Super Kamiokande and Arthur MacDonald of SNO for the discovery of neutrino oscillations, which demonstrated that neutrinos have mass. These prizes recognize one of the most important discoveries in particle physics. A discovery that required overturning a fundamental assumption of the Standard Model, and that took more than 40 years from the first anomalous measurement to the definitive resolution. Since these landmark discoveries, neutrino detection has continued to advance in ambition and scale. And perhaps the most remarkable detector operating today is one that uses a cubic kilometer of Antarctic ice as its detection medium. IceCube is located at the Amundsen Scott South Pole Station, at the geographic South Pole in Antarctica. But the detector itself is not on the surface. It's buried deep within the Antarctic ice sheet, at depths ranging from 1,450 to 2,450 meters below the surface. The detector consists of 5,160 digital optical modules, essentially basketball-sized glass spheres, each containing a photomultiplier tube and associated electronics, strung along 86 vertical cables embedded in the ice. These cables were deployed by drilling holes into the ice using powerful hot water drills, lowering the strings of optical modules into the holes, and then allowing the ice to refreeze around them, locking the sensors permanently in place. The result is an instrumented volume of roughly 1 cubic kilometer of crystal clear Antarctic ice. 1 full cubic kilometer. The ice at these depths is under tremendous pressure and is remarkably transparent. Photons of Cherenkov light can travel over 100 meters through it before being absorbed. When a high-energy neutrino interacts with an atom in the ice, an oxygen or hydrogen nucleus in the frozen water molecules, the resulting charged particle produces a trail of Cherenkov light that the optical modules detect. From the pattern of light, which modules were triggered, in what order, with what intensity, physicists can reconstruct the energy and direction of the original neutrino with surprising precision. IceCube was designed to detect neutrinos at energies far beyond what Super Kamiokande or SNO can reach. Solar neutrinos have energies of a few million electron volts. IceCube targets neutrinos with energies in the billions to quadrillions of electron volts. Tera electron volt and peta electron volt neutrinos produced by the most violent processes in the universe. At these extreme energies, the neutrino interaction cross-section is much larger than at solar neutrino energies, which makes detection feasible even though the flux of such high-energy neutrinos is far lower. In 2013, IceCube announced the detection of 2 neutrinos with energies exceeding 1 peta-electron volt, 1 quadrillion electron volts, which the collaboration affectionately named Bert and Ernie. These were by far the highest energy neutrinos ever observed, carrying roughly 1 million times more energy than any neutrino produced by a particle accelerator on Earth. Their origin was clearly astrophysical. They came from somewhere out there in the cosmos, produced by processes of extreme violence and power. Then, in September of 2017, IceCube detected a high-energy neutrino and quickly sent out an alert to observatories around the world. Telescopes across the electromagnetic spectrum, gamma-ray, X-ray, optical, radio, swiveled to look at the patch of sky the neutrino had come from. What they found was a blazar, a galaxy roughly 4 billion light-years from Earth, with a supermassive black hole at its center that was shooting a jet of relativistic matter and energy almost directly toward us. The blazar, designated TXS 0506 plus 056, was in a flaring state, producing intense gamma radiation. The neutrino had come from this blazar. For the first time in history, a high-energy cosmic neutrino had been traced to a specific astrophysical source outside our solar system. This was a watershed moment. It marked the true birth of high-energy neutrino astronomy, using neutrinos not just as tools to study particle physics, but as messengers to observe the universe itself. Photons have been our primary, astronomical messenger for all of human history. Gravitational waves, first detected in 2015, added a second messenger. Neutrinos are the third, and they carry information that neither photons nor gravitational waves can provide, because they emerge unscathed from environments so dense and violent that light cannot escape. The detectors we've built to catch neutrinos are among the most extraordinary scientific instruments ever constructed. A tank of cleaning fluid in a gold mine, 50,000 tons of ultra-pure water watched by 11,000 light sensors in a Japanese zinc mine, 1,000 tons of heavy water worth hundreds of millions of dollars suspended in an acrylic vessel 2 kilometers underground in a Canadian nickel mine, a cubic kilometer of Antarctic ice instrumented with 5,000 sensors at the bottom of the world. Each of these detectors represents an enormous investment of human ingenuity, resources, and patience, all dedicated to catching a particle that barely acknowledges our existence. And each one has told us something we couldn't have learned any other way. Davis taught us the sun's neutrinos were real, but something unexpected was happening to them. Super Kamiokande taught us neutrinos change flavor and therefore have mass. SNO taught us the sun works exactly as predicted, and that every missing neutrino was accounted for. Ice Cube taught us the cosmos screams in neutrinos from the hearts of the most extreme objects in the universe. The question now is what neutrinos are going to teach us next. Because if history is any guide, the ghost particle still has secrets to reveal. Secrets about the death of stars, the birth of the universe, and perhaps even the reason why anything exists at all. On February 23, 1987, something extraordinary happened. A blue supergiant star in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, located about 168,000 light years from Earth, reached the end of its life. The star, catalogued as Sanduleak negative 69202, had been burning through its nuclear fuel for roughly 20 million years. It had fused hydrogen into helium, helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. And iron is where the road ends. Iron fusion doesn't release energy, it consumes it. When the star's core became a ball of iron, roughly the mass of our sun, but compressed into a region only a few thousand kilometers across, it could no longer support itself against its own gravity. In a fraction of a second, the core collapsed. What happened next released more energy than the human mind can meaningfully comprehend. The core imploded from a few thousand kilometers across to a sphere roughly 30 kilometers in diameter, a newborn neutron star, in less than a second. The gravitational potential energy released by this collapse was approximately 3 times 10 to the 46 joules. That is more energy than our sun will produce in its entire 10 billion year lifetime. And roughly 99% of that energy, not half, not most, but virtually all of it, was carried away by neutrinos. The visible explosion, the shockwave that tore the star apart, the brilliant flash of light that would soon be visible across intergalactic space, all of that was powered by the remaining 1%. The neutrinos escaped first. They had to. The collapsing core produced a flood of neutrinos of all flavors in unimaginable quantities. Roughly 10 to the 58 neutrinos released in a burst lasting about 10 seconds. These neutrinos streamed outward from the core at nearly the speed of light, passing through the outer layers of the dying star as if those layers were empty space. The light, by contrast, had to wait. The shock wave generated by the core bounce, the rebound of infalling matter off the newly formed neutron star, took hours to travel outward through the star's massive envelope and break through the surface. Only then did the star begin to brighten visibly. 3 neutrino detectors on Earth registered the event. Kamiokande 2 in Japan detected 12 neutrinos over a span of about 13 seconds. The Irvine, Michigan Brookhaven detector in Ohio detected 8. The Baksan Neutrino Observatory in Russia detected 5. 25 neutrinos in total, captured within a window of roughly 13 seconds. That's all. 24 particles from an event that released 10 to the 58 of them. 24 might not sound like much, but consider what those 24 neutrinos represent. They traveled 168,000 light-years across intergalactic space from a galaxy beyond our own, covering a distance of roughly 1.59 times 10 to the 18th kilometers. They arrived at Earth and passed through the planet's entire mass, continuing through rock and metal and ocean as if none of it existed. And out of the trillions that passed through each detector, a handful, just a handful, happened to interact with atoms in the water or scintillator fluid inside those instruments. The probability of any individual neutrino interacting was absurdly small, but the sheer number of neutrinos was so staggering that a few interactions were statistically inevitable. Those 25 detections were the inevitable residue of an almost inconceivably large number, filtered through an almost inconceivably small probability. And those 24 neutrinos arrived approximately 3 hours before the first visible light from the supernova was observed by astronomers in the southern hemisphere. 3 hours. The neutrinos carried news of the core collapse while the shock wave was still fighting its way through the star's outer layers. By the time telescopes spotted the brightening star, the neutrinos had already told us what happened. They were the heralds, the advanced messengers of stellar death. The detection of neutrinos from supernova 1987A was a triumph of both theory and experiment. For decades, astrophysicists had built models of how massive stars die. The models predicted that the core would collapse, that a neutron star would form, that an enormous burst of neutrinos would carry away most of the energy, and that a shock wave would follow, producing the visible explosion. The 1987A neutrinos confirmed this picture with stunning directness. The energies of the detected neutrinos match predictions. The duration of the burst, about 13 seconds, matched the expected timescale of neutron star formation and cooling. The total energy implied by scaling up from 24 detected neutrinos to the full flux was consistent with the predicted 3 times 10 to the 46 joules. Everything fit. Our models of stellar death were correct, and neutrinos had proven it. Masatoshi Kashiba shared the 2002 Nobel Prize in Physics, in part for the detection of these supernova neutrinos at Kamiokande 2. It was a recognition not just of a single measurement, but of the birth of a new way of observing the universe. And that's what neutrino astronomy truly represents. A fundamentally new sense with which to perceive the cosmos. For almost all of human history, we study the universe through one channel: electromagnetic radiation, visible light from the earlier stargazers, radio waves from the 1930s onward, infrared, ultraviolet, X-rays, and gamma rays as our instruments expanded across the electromagnetic spectrum. Every telescope ever built, from Galileo's simple refractor to the James Webb Space Telescope, detects some form of light, and light has taught us an extraordinary amount about the universe. But light has limitations. Photons interact electromagnetically, which means they can be blocked, absorbed, scattered, and distorted by matter between the source and the observer. Dense clouds of gas and dust obscure our view of the galactic center. The interiors of stars are completely opaque. The early universe, before about 380,000 years after the Big Bang, was an opaque plasma through which no photon could travel freely. There are entire realms of the cosmos that light simply cannot show us. Neutrinos have no such limitation. Because they interact only through the weak force, the matter that blocks light is utterly transparent to them. They stream directly out of the cores of stars, the hearts of supernovae, and the violent environments around black holes without being impeded. When we detect a neutrino from an astrophysical source, we're receiving a message that has traveled in a straight line from the source to our detector, unscattered and unabsorbed, carrying pristine information about the conditions at the point of origin. The ice cube detection of a neutrino from the blazar, TXS 0506 plus 056, in 2017 was one milestone in this emerging field. But it's just the beginning. Future neutrino telescopes, larger, more sensitive, deployed at new sites around the world, will dramatically expand our ability to observe the universe through neutrino eyes. KM3NET, currently under construction in the Mediterranean Sea, will instrument several cubic kilometers of deep sea water with thousands of optical sensors. The Baikal G-VD detector in Lake Baikal, Russia, is already operational and growing. The proposed Pacific Ocean neutrino experiment would instrument an enormous volume of deep ocean water off the coast of Canada. Each of these next-generation detectors will be able to detect neutrinos from more distant and fainter sources, mapping the high-energy neutrino sky with increasing precision. But perhaps the most extraordinary neutrino signal we might someday detect is one that has been traveling toward us for almost the entire history of the universe: the cosmic neutrino background. You've probably heard of the cosmic microwave background, the faint glow of radiation that fills all of space, a relic of the era about 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. The cosmic microwave background was discovered in 1965 by Arno Penzias and Robert Wilson, and it has become one of the most powerful tools in cosmology, giving us a snapshot of the infant universe. But the cosmic neutrino background is older, much older. It dates not to 380,000 years after the Big Bang, but to about 1 second after the Big Bang. In that first second, the universe was inconceivably hot and dense. Temperatures exceeded 10 billion degrees Kelvin. Matter and radiation were in constant violent interaction. Neutrinos were being created and annihilated in vast numbers, maintained in thermal equilibrium with the surrounding plasma of quarks, electrons, photons, and other particles. The weak force, despite its feebleness under normal conditions, was effective at these extreme energies because the high temperatures meant particles had enough energy to readily create the massive W and Z bosons that mediate weak interactions. But as the universe expanded, it cooled. And as it cooled, the average energy of particles dropped. About 1 second after the Big Bang, the temperature fell below the threshold at which weak interactions could keep neutrinos in equilibrium with the rest of matter. The neutrinos decoupled. They stopped interacting. And from that moment forward, they have been streaming freely through the universe, a ghostly imprint of conditions as they were just 1 second after the beginning of everything. Those neutrinos are still here. They've been traveling for 13.8 billion years, cooling as the universe expanded, their wavelengths stretching, their energies dropping to minuscule values. Today, the cosmic neutrino background has an estimated temperature of about 1.95 Kelvin, roughly negative 271 degrees Celsius. That's even colder than the cosmic microwave background, which sits at about 2.7 Kelvin. The estimated density is about 336 neutrinos per cubic centimeter, everywhere in the universe. Right now, in the air around you, in the space between the atoms of your body, in the vacuum between galaxies, there are roughly 336 primordial neutrinos per cubic centimeter drifting through the cosmos as relics of the first second. We haven't directly detected them yet. Their energies are so fantastically low, far below the threshold of any current detector, that catching one is beyond our present technology. But physicists are working on it. The Ptolemy experiment, proposed at Princeton University, aims to detect cosmic relic neutrinos by looking for a subtle signature in the beta decay of tritium, a radioactive isotope of hydrogen. When a tritium nucleus decays, it normally produces a helium-3 nucleus, an electron, and an antineutrino. The electron's energy is determined by the energy balance of the reaction. But if a relic neutrino from the cosmic background happens to be captured by the tritium nucleus during the decay, a process called neutrino capture on tritium, the electron would emerge with slightly more energy than the maximum normally allowed. Detecting this tiny energy excess would be a direct detection of the cosmic neutrino background. If Ptolemy or a similar experiment succeeds, it will give us direct observational access to the universe as it was 1 second old. 1 second. The cosmic microwave background, as powerful as it is, only shows us the universe at 380,000 years. The cosmic neutrino background would push our observational window back by a factor of roughly 12 million to an epoch when the universe was a cauldron of primordial particles, before any atoms existed, before any structures had formed, when the cosmos was pure energy and matter in violent equilibrium. It would be the earliest direct observation of the universe ever made. Beyond what neutrinos have already taught us, there are profound open questions that neutrino physics may help answer. Questions that strike at the deepest foundations of particle physics and cosmology. The first and most fundamental: what is the actual mass of each neutrino flavor? Oscillation experiments have told us the differences in mass squared between the flavors, but not the absolute mass of any individual flavor. We know that at least 2 of the 3 flavors have non-zero mass. We know the approximate differences, but we don't know the overall mass scale, and we don't know the ordering. Is the electron neutrino the lightest, with the muon and tau neutrinos progressively heavier? This is called the normal hierarchy. Or is the electron neutrino the heaviest, with the other 2 lighter? This is the inverted hierarchy. The answer matters for cosmology, for models of the early universe, and for our understanding of fundamental particle physics. Several major experiments are being built to address this question. Juno, the Jiangmen Underground Neutrino Observatory in China will use 20,000 metric tons of liquid scintillator to study reactor antineutrinos with unprecedented precision, aiming to determine the mass hierarchy. DUNE, the Deep Underground Neutrino Experiment in the United States, will fire an intense beam of neutrinos from Fermilab in Illinois to a massive liquid argon detector 1,300 kilometers away in the Sanford Underground Research Facility in South Dakota. The same mine where Raymond Davis conducted his pioneering experiment decades earlier. DUNE aims to measure neutrino oscillation parameters with enough precision to determine the mass ordering definitively. The second question is perhaps even more profound. Are neutrinos Dirac particles or Majorana particles? Every other known fermion, every quark, every charged lepton is a Dirac particle, meaning the particle and its antiparticle are distinct entities. An electron is not a positron. A proton is not an antiproton. They're different objects with different charges. But neutrinos are unique among known fermions because they carry no electric charge. This means there is no charge to distinguish a neutrino from an antineutrino. It's possible that neutrinos are their own antiparticles. That the neutrino and the antineutrino are the same particle. Such particles are called Majorana fermions, after the Italian physicist Ettore Majorana, who proposed the concept in 1937 before mysteriously disappearing at the age of 31. If neutrinos are Majorana particles, it would have far-reaching consequences for physics. It would imply the existence of a new mechanism for generating neutrino mass, different from the mechanism that gives mass to all other fermions. It would also open the door to explaining one of the deepest mysteries in cosmology: why the universe exists at all. The way to test this is to search for a process called neutrinoless double beta decay. In ordinary double beta decay, two neutrons in a nucleus simultaneously convert into protons, emitting two electrons and two antineutrinos. This process is extremely rare, but has been observed. In neutrinoless double beta decay, the same transformation occurs. Two neutrons become two protons and two electrons, but no neutrinos are emitted. This is only possible if the neutrino is its own antiparticle, because the antineutrino emitted by one decay is absorbed as a neutrino by the other. The two neutrinos effectively cancel each other out. If this process exists, it would prove that neutrinos are Majorana particles. Several experiments around the world are searching for neutrinoless double beta decay with increasing sensitivity. Legend, using germanium detectors, is operating in stages in Italy. Nexo proposes to use 5,000 kilograms of enriched xenon in a liquid xenon detector. Cupid will use lithium molybdate scintillating bolometers, cooled to near absolute zero. So far, no confirmed detection has been made, but the experiments are pushing to sensitivities that probe deeper and deeper into the allowed parameter space. If neutrinoless double beta decay exists, we may find it within the next decade or two. The third and perhaps most awe-inspiring question is whether neutrinos can explain why we exist. This sounds dramatic, but it's a genuine and precise scientific question. The Big Bang should have produced exactly equal amounts of matter and antimatter. Every time a particle was created, its antiparticle should have been created alongside it. And when matter and antimatter meet, they annihilate completely, converting into pure energy. If the universe had started with perfect symmetry between matter and antimatter, everything would have annihilated. The universe would contain nothing but a diffuse bath of photons and neutrinos, no atoms, no stars, no planets, no life, nothing. But that's not what happened. Somehow there was a tiny imbalance, roughly one extra matter particle for every billion matter-antimatter pairs. That tiny excess, that 1 in a billion asymmetry, is everything. Every atom in the universe, every star, every planet, every living thing, all of it is that leftover sliver of matter that survived the Great Annihilation. Something must have created this imbalance. Physicists call the required conditions the Sakharov conditions, after the Russian physicist Andrei Sakharov, who identified them in 1967. One of these conditions is CP violation, a difference in how the laws of physics treat matter versus antimatter. CP violation has been observed in the quark sector. Quarks and antiquarks behave slightly differently under certain transformations, but the amount of CP violation observed in quarks is far too small to account for the matter-antimatter asymmetry we see in the universe. Something else must be contributing. Neutrinos might be that something else. If there is significant CP violation in the neutrino sector, if neutrinos and antineutrinos oscillate differently, it could have influenced the balance of matter and antimatter in the early universe through a theoretical mechanism called leptogenesis. In this scenario, heavy Majorana neutrinos in the early universe decayed in a CP violating way, producing slightly more leptons than antileptons. This lepton asymmetry was then partially converted into a baryon asymmetry, more protons and neutrons than antiprotons and antineutrons, through processes in the early universe that interconvert leptons and baryons. The result? The tiny matter excess that eventually became everything. Dune is specifically designed to search for CP violation in neutrino oscillations. By comparing how neutrinos and antineutrinos oscillate over the same distance, Dune can measure whether there's a difference, whether the universe treats neutrinos and antineutrinos differently. If it finds significant CP violation, it would be a major step toward understanding why the universe contains matter at all. It wouldn't prove leptogenesis by itself, but it would show that the neutrino sector has the right properties to make leptogenesis work. It would suggest that the reason anything exists, the reason there are atoms and stars and planets and people, might trace back to a subtle asymmetry in the behavior of the universe's most ghostly particle. There's one more question worth mentioning. Are there neutrino types beyond the three we know? The electron neutrino, muon neutrino, and tau neutrino all interact through the weak force, which is how we detect them. But some theoretical models and some intriguing but inconclusive experimental hints over the years have suggested there might be a fourth type, a sterile neutrino, that doesn't interact through the weak force at all. A sterile neutrino would interact only through gravity, making it even more ghostly than ordinary neutrinos. If sterile neutrinos exist with the right mass, they could be a component of dark matter, the mysterious substance that makes up about 27% of the universe's total energy content and whose identity remains one of the biggest unsolved problems in all of physics. The search for sterile neutrinos is ongoing, with experiments like Microboon and the short baseline neutrino program at Fermilab probing the parameter space where they might hide. When you step back and look at the full picture, what emerges is something remarkable. The neutrino, a particle that barely participates in the universe, that passes through stars and planets without noticing, that can fly through a light year of solid lead with a coin flip chance of surviving, has become one of the most powerful tools we have for understanding reality. Its very elusiveness is what makes it valuable. Because neutrinos interact so rarely, they carry information from places that no other particle can escape. The core of a collapsing star, the first second after the Big Bang, the hearts of blazers billions of light years away. Neutrinos are messengers from the unreachable, witnesses to events that no other form of matter or radiation can report on. And we, small beings on a small planet, orbiting an ordinary star in a spiral galaxy that is one among trillions, figured out how to catch them. We deduced their existence from a subtle energy discrepancy in radioactive decay. We predicted their properties using mathematics and quantum field theory. We buried tanks of cleaning fluid and ultra-pure water deep inside mines. We instrumented a cubic kilometer of Antarctic ice with thousands of light sensors. We waited, sometimes for decades, for the faint statistical signal to emerge from the noise. And it worked. We detected the undetectable. We observed the nearly unobservable. Right now, as you listen to these final words, roughly 100 trillion neutrinos are passing through your body every second. They are streaming through your skin, your bones, every atom you are made of. They come from the fusion reactions in the heart of the sun. They come from cosmic ray collisions in the atmosphere above you. They come from radioactive decays in the earth beneath you. They come from nuclear reactors on distant continents. They come from supernovae that exploded in galaxies you will never see. And roughly 336 of them, in every cubic centimeter of space around you, have been drifting since 1 second after the Big Bang. Ancient travelers from the birth of the cosmos, still wandering, still silent, still passing through everything they encounter. Not one of them will touch you. You will never feel their presence. The electromagnetic force that builds your body and shapes your world has no hold on them. They exist in a realm of physics that your senses were never designed to access. And yet, you know they are there. You understand what they are, where they come from, and why they pass through everything. You've grasped a truth about the universe that is invisible, intangible, and accessible only through the power of a human reasoning. The neutrino doesn't know you exist. It has no awareness, no intent, no knowledge of the matter it passes through. But you know it exists. And in the quiet contest between a particle that passes through everything and a mind that seeks to understand everything, the mind wins. Not by stopping the neutrino, nothing truly can, but by knowing it's there, by measuring it, by using it to see the hidden architecture of stars, the mechanics of stellar death, the structure of the early universe, and perhaps, someday, the reason why matter won its ancient war against antimatter and the cosmos, filled with atoms instead of emptiness. That is the story of the neutrino, born from a desperate idea to save energy conservation. Named affectionately in Italian, hunted for 26 years before being caught beside a nuclear reactor, found to change identity in flight, overturning decades of assumption, used to peer inside the sun to witness the death of a star in a distant galaxy, and to observe the most violent objects in the cosmos, and still holding secrets about its own mass, about whether it is its own antiparticle, about whether it is the reason anything exists at all. The universe built a particle that barely participates in reality as we experience it. And then, on one small world, reality built something that could notice. The ghost particle and the curious species, both made of the same atoms, forged in the same stars, governed by the same laws. One passes through everything. The other tries to understand everything, and somehow, improbably, beautifully, they found each other. So tonight, when you look up at the stars, remember what's invisible. The neutrinos streaming from every point of light you see, crossing the vast distances between those stars and your eyes at nearly the speed of light, carrying news from nuclear furnaces you'll never visit. Remember the ones coming up through the ground beneath your feet, born in the radioactive decay of ancient rocks. Remember the ones from the Big Bang itself, 336 in every cubic centimeter, older than the stars, older than the galaxies, older than almost everything that exists. They are all around you. They are always passing through. And now you know what they are, and why the universe lets them through. Thank you for joining me on this journey into the invisible. If you found it worthwhile, a like or subscribe means more than you know. It helps me keep making these explorations. And the next time you hold up your hand and realize that 65 billion neutrinos just passed through your thumbnail in the last second, give them a thought. They've come a long way, from the heart of a star, across 150 million kilometers of empty space, through the atmosphere, through the roof above your head, and through you. They won't stop. They never do. But at least now, you know they're there. Good night. And sleep well, knowing the universe's gentlest particles are keeping you company, even if they'll never say hello.